The interaction picture is one of the most important parts of quantum field theory in the operator formalism. The reason why it's so important is it allows you to do interacting quantum field theory with mathematics that is a little more complicated than that used in free quantum field theory. The fundamental reason why this is in the interaction picture, interacting quantum fields take the mathematical form of free fields in the old Heisenberg picture. And they even satisfy the same equal time commutation or anti-commutation relations. And therefore the fact that from the interaction picture you can derive a very convenient expression for the S operator and therefore the S matrix means that it's extremely conducive to doing practical calculations in quantum field theory. In this video, I'm going to derive the interaction picture, and then from the interaction picture I'm going to derive the S operator and therefore the S matrix. This is a key step in the process of going from a Lagrangian to actual physical predictions. There's really no way to get into quantum field theory without understanding this. So watch this comprehensive video carefully if you want to understand quantum field theory. Here follows the math section where I actually give a treatment of this bit of theory. In quantum field theory, it is a bit of a lengthy process to go from the classical action of a given quantum field theory to actual physical predictions like scattering cross-sections and decay rates. There are two commonly used ways. The first is the operator method, and the second is the path integral method. The path integral method is not discussed here. However, one step in the operator method is shown in detail. The entire operator method consists of three main concepts which ultimately allow for the perturbative calculation of the S matrix from quantum field theory. The first concept is the use of the interaction picture to derive an expression for the S operator, which is important because it has the following property given by this equation. The S operator time evolves the initial state to infinite time, a good approximation for measuring the output far away from the interaction. I will refer to this time of measurement, which is approximated by infinity, as the output time. One can then say that the S operator time evolves the initial state to the output time, at which point it is some superposition of possible final eigenstates, and one can take the inner product with one such final state to find the probability amplitude that the input state has scattered into that particular final state. That's what's encoded in this equation here. Matrix elements of the S operator of this type form what is called the S matrix, where S is short for scattering in all of this. To understand the point of the second key concept, one must note that the S operator involves time-ordered products. Now, it's not obvious from this equation that that's the case, but we'll find in our analysis where we derive the S operator that that's the case. The second key concept is Wick's theorem, which allows arbitrarily complicated time-ordered products to be written as normal-ordered products and two-point Green's function. The third concept is the LSZ reduction. This allows matrix elements between populated states to be written in terms of vacuum matrix elements of time-ordered field operators. If all three of these concepts are applied together, one can perturbatively calculate the S matrix of a theory from the action. This is done by expanding the S operator in the matrix element and then applying the LSZ reduction formulas, and then Wick expanding it all. Physical quantities can then be written in terms of the S matrix. Handling all of this in one video is unreasonable, so only the derivation of the interaction picture and the S operator will be done here. The idea of the interaction picture is to formulate quantum mechanics or quantum field theory such that time evolution is accounted for by allowing both the operators and state vectors to be time dependent. The useful catch is that the time dependence of the state vectors and operators are entirely dictated by different parts of the Hamiltonian. Specifically, the interacting Hamiltonian dictates the time evolution of the state vectors, and the free Hamiltonian dictates the time evolution of the operators. In this section, the interaction picture time evolution equations are derived, and the most useful formula for the S operator is then derived from the interaction picture. The interacting quantum fields, field operators, take the form of free fields in the interaction picture and still satisfy the usual equal time commutation or anti-commutation relations, depending on whether you're dealing with fermions or bosons. This is what makes interacting quantum field theory in the interaction picture tractable, and why the interaction picture is the standard picture for interacting quantum field theory. Free field quantization is typically done with the Heisenberg picture, where the states are time independent and the time dependence of the system is carried by the operators, namely the field operators like phi of x and t. In the Heisenberg picture, the time dependence is governed by the Heisenberg equations of motion. given here. Alternatively, one could use the Schrödinger picture. In this picture, the state vectors carry the time dependence and the operators are time independent. Specifically, the time dependence of the states is governed by the generalized Schrödinger equation, which is given here also in natural units. One can therefore write this relationship between the Schrödinger states and the Heisenberg states by solving this equation and recognizing the time independence of the Heisenberg states. The operators in the Heisenberg and Schrödinger picture are related to each other in this way. The reason why that is because that's what solves this equation up here. When dealing with interactions, neither the Heisenberg nor the Schrödinger picture are convenient to work with. The picture that is convenient to work with is called the interaction picture and is somewhere between the two. It's sometimes also called the Dirac picture. In this picture, both state vectors and operators carry time dependence, but their time dependence is governed by different parts of the Hamiltonian. To construct the interaction picture, one starts by splitting up the Hamiltonian into a free and interacting part. H naught here is the free part and H prime is the interacting part. I don't use a subscript I for the interacting Hamiltonian because that will be used in this document to denote the interaction picture. Specifically, the time dependence of the operators is governed by the free Hamiltonian and the time dependence of the states is governed by the interacting Hamiltonian. To construct this, one starts by making a few definitions. These definitions here, and we'll see that these definitions are the right ones because they're the ones that yield the nicest equations of motion. Specifically, the equations of motion will not just take a nice form, but the time dependence of these two things will be controlled exclusively by the two separate parts of the Hamiltonian described up here. The goal is to find the time evolution equations for the operators and states in the interaction picture. Once we've done that, we will have finished formulating the interaction picture and we can move on to trying to derive the S operator from it. To find the time evolution equations for the states, one can apply the Schrödinger equation for Schrödinger picture states to derive a time evolution equation for the interaction picture states. If we simply time differentiate the interaction picture quantum states and then recognize the Schrödinger equation for Schrödinger picture states, we see that we can rewrite this last term in a compelling way. So we substitute this term for this value here, that gives us this, then we expand out the Hamiltonian there and realize that there's a useful cancellation between the free parts, and then we insert this operator and its inverse in this product here, and then remember these definitions. Inserting these definitions gets us here. We now have an equation of motion for the interaction picture states that has no reference to any other picture and where the time evolution is controlled exclusively by the interacting Hamiltonian. This is exactly what we were looking for, and this is one of the key equations defining the interaction picture. The next task is to find the time evolution equation for the interaction picture operators. Given that the time dependence of the interaction picture operators is governed purely by the free Hamiltonian, the interaction picture operators satisfy the Heisenberg equation of motion with the free Hamiltonian. This is not only intuitively clear, but one can insert this definition into that equation and one finds that it is satisfied. Because we now have the equation of motion for the operators, we have completed the derivation of the interaction picture. Now, if you'd find it more satisfying to do a more direct derivation of this equation, where I don't just appeal to intuition to write it down and then confirm it by plugging in this value and showing that it's solved, you can actually do the derivation much like we did above, where we take this operator and just time differentiate it, and then use identities that we already have in order to rewrite that time derivative like this right side here. Both ways of doing it work. They both verify that this is the correct operator equation. It just depends on your taste. I did a direct method for the interaction picture states, and then I used the intuition and confirm approach for this one, but you can just as easily do a more direct method for the operator equation as well. Now this can be applied to interacting quantum field theory to yield a formula for the S operator. But before we actually do that, I want to show you that the interaction picture actually is ideal for quantum field theory. I asserted it above, and I gave the reasons, but I didn't show those reasons to be true. I didn't actually demonstrate them. So really, so far, all I've done is assert that the interaction picture is the right one for quantum field theory, and then I've derived it. I have not yet explained truly, or rather shown, why it actually is right, in that I didn't actually justify the reasons that I gave. Now that we have the interaction picture, its appropriateness for interacting quantum field theory can be shown. This display comes in two parts. First, it can be shown that interacting quantum fields in the interaction picture satisfy the same equal-time commutation relations, or anti-commutation relations for fermions, as their Heisenberg picture counterparts. This will be shown in a minute. And second, because we found that the time evolution of the interacting quantum fields in the interaction picture is purely governed by the free Hamiltonian, the interacting quantum fields satisfy the same free equations in motion as the fields in a truly free theory in the Heisenberg picture, despite the interaction term in the Lagrangian density. We can see that here. If we have the interaction picture, even in the presence of an interaction term, this is still going to be the free Hamiltonian. And if we take the case of the Heisenberg picture, where we're in a free theory, then all you have is the free Hamiltonian. The entire Hamiltonian is just the free Hamiltonian, so these equations end up being identical. So if we take phi to the fourth theory as an example, we have this Lagrangian density. The equivalence of these two equations of motion implies this for that theory, and therefore this, because we're just solving the free equations. This makes the interaction picture favorable because it expresses the interacting quantum fields with the same familiar and easy to handle mathematical structure as free quantum fields in the Heisenberg picture. In the Heisenberg picture, the field operators satisfy the full interacting Euler-Lagrange equations, and it is therefore unclear how to handle the interacting quantum field theory. This is the fundamental benefit of the interaction picture. Let us now return to that first piece, which is proving the validity of the same commutation relations. This proof will be done for the case of scalar bosons. Other cases are trivial generalizations of the same calculation. Let's start with the operator relations to the Schrödinger picture from above. We have the relation between the interaction picture operators and the Schrödinger picture operators, and the Heisenberg picture operators and the Schrödinger picture operators. From this, we can develop a relationship between the interaction picture operators and the Heisenberg picture operators. This operator here that we get that converts those two will be dominating our lives for basically the entire rest of the problem, because it's ultimately where the S operator is going to come from, and therefore the foundation of the S matrix. So it's useful to develop a shorthand notation for it. We'll call this operator U. Therefore, this relation between the interaction picture operators and the Heisenberg picture operators looks like this. Now, applying this operation to the Heisenberg picture equal time commutation relations ultimately gets us here. Specifically, if we just apply it to both sides, and of course this is just a number, so it passes right through them and they cancel. And then if we look at the operator products here, we can simply handle those by first distributing these through and then sticking a factor of the identity written as U inverse U inside each of these two products. Then that converts them to the interaction picture fields, and we arrive at the same commutation relations. So we've shown the validity of this commutation relation in the interaction picture. What that means is the interacting quantum fields in the interaction picture not only take this form and satisfy this free equation, but they satisfy the same equal time commutation relation. So really, we are dealing with exactly the same mathematical structure as we were in the free theory in the Heisenberg picture, but with an interacting theory in the interaction picture. And that's why the interaction picture is so important. So now let's review a little bit. I realize this is a lot to keep track of. What has been accomplished so far in this document is the following. We have derived the interaction picture, and we have shown that it has the potential to make interacting quantum field theory doable. With this done, we can now focus on extracting the scattering operator, S operator, and by default the scattering matrix, S matrix, from the interaction picture. It might seem random, but the key to doing this lies in a careful analysis of this U operator that we dealt with previously. Specifically, we will look for a new and revealing expression for it. Why this is the correct thing to do will become apparent as we work through the analysis. Our analysis will take the following course. First, we will derive a differential equation that is solved by the U operator using the formula we already have for it right there, and then we will solve it for a new form of it, and we will rework this solution into the form of a so-called time-ordered exponential. Studying this formula for the U operator will reveal the S operator. Now let's find the differential equation satisfied by the U operator that I mentioned above. And we can do this by directly using the product rule and remembering that undesignated Hamiltonians in this particular case are in the Schrödinger picture and therefore are time independent. We ultimately arrive at this result here. However, if we remember the relation between the interacting Hamiltonian in the interaction picture and its version in the Schrödinger picture, we find that we can rewrite that quantity like this. And therefore we have this nice differential differential equation for the u operator that we can deal with. This equation can be solved for a new expression for u. The way to do this is to integrate the equation with respect to time and eventually iterate it to get an explicit solution. Doing this directly gives this. Now we need to figure out what the integration constant needs to be, and as always when you integrate a time differential equation, you use initial conditions to do that. We already have this formula for the u operator, so we can look at what it is at t equals 0, and we find it's just the identity. Taking t equal to 0 for this, we find that this quantity necessarily vanishes because we're integrating over no interval, so that means c1 just has to equal the identity. With this inserted, we find this expression for u. We can then use this to express u of t1. Doing that gives us this expression for it, where t2 must never exceed t1 because it is the integration limit. One can then insert u of t1 into u of t to get this. If the substitution process is performed an infinite number of times, one finds the following expression for u of t, this one. The point of iterating it like this is that we now have an explicit solution instead of one defined in terms of itself, and it leads to a final answer that is very useful in practical calculations. Specifically, with a little bit more effort, we can get it to yield the S operator. Now, looking at the third term for a moment, we can rewrite it with less specific integration limits if the same condition maintained by the specific integration limits is imposed by a theta function, a step function, specifically the Heaviside theta function, and the specific condition is, as I said above, t2 must never exceed t1. Doing that gets us here. However, because the integration variables are dummy variables, one can cleverly but ultimately trivially relabel them. So if we replace these with newly labeled versions where we take these tildes to be t2 and t1, and then recognizing that we must also flip the condition we had on them, that t1 must now never exceed t2, then we can get this expression for it, and we once again can make the integration limits less specific with this theta function. We can then combine these two to get this. However, now we see a time-ordered product here. So it may have seemed extremely strange that we were doing all that weird index relabeling and work with the integration limits and the theta functions, but this is what we were after, this time-ordered product form of this term. This is the previously mysterious fundamental point of doing that rewriting. We can then perform this same procedure for all the terms in the series, where we don't just end up with 2 that we need to sum. With a factor of 2, we end up with n factorial of them, because there are a progressively larger number of integrations and integration variables to play with. So then the final answer has that n factorial in the denominator. And this is ultimately how we're going to get a time-ordered exponential out of this. If we plug this into the full expression for the u operator, meaning we just sum the terms, then we arrive here. This object, of course, is just a time-ordered exponential, where the time ordering just denotes that all the terms in the Taylor expansion must be time-ordered. So now we have that u operator expression we were looking for in terms of the time-ordered exponential. One can pick any reference time to start the integration. We don't have to call that time t equals 0, so just sticking a t0 in there and expanding the variable dependence gives us what we're looking for. If we write this in terms of the Hamiltonian density, then we arrive at this expression for the u operator. With this finished, what we need to do in order to proceed to the s operator is figure out what this u operator is. I've done all these formal manipulations on the u operator with the promise that it was going to yield the s operator, but to date none of the manipulations I've done, however interesting, actually show you what the u operator does aside from interconvert between the Heisenberg and interaction picture. It has a much more fundamental use, and we can figure that out by studying the interaction picture states. So because of that, focus must shift back to the interaction picture state vectors. One can perform essentially the same calculation on them, and this gives us the critical result that this u operator actually time evolves the states of the theory. This gets us one step closer to arriving at the s operator. We will start with the equation of motion satisfied by the interaction picture quantum states, in analogy to starting with the equation of motion of the u operator when we were deriving a desirable expression for that. Above, we saw that the equation of motion for the interaction picture quantum states is this. So now we can solve that just like we did for the u operator. Also, like in the case of the u operator, we can use the same iteration process to write the exact solution as a time-ordered exponential like this. And now we get to the key here. We simply arrive at the fact that the u operator that we explored above time evolves the states. This is the fundamental use of the U operator. This is one of the most important punchlines here. This fact is why we bothered to explore the U operator so thoroughly in the first place. It turns out that the elusive S operator that we seek is a special case of the U operator precisely because it has this role of time-evolving states. From now on, I will call the U operator the time evolution operator for obvious reasons. Let's find its relation to the S operator now. For scattering calculations, one considers the case where the initial state is at time equals negative infinity, and where you're actually doing the measurement is at time equals to positive infinity. As I explained earlier, these infinite times simplify the math and are a good approximation for real experiments, where initial states are prepared very far from the interaction location and measurements are also made far away. The region where the scattering is taking place is microscopic, so the macroscopic distances separating the different parts of the experiment are effectively infinite. Using these state definitions and the time evolution operator, we can write the following results. We can evolve the initial state at negative infinity to some time t with this U operator, and we can just integrate all the way to t equals infinity to evolve the initial state from negative infinity all the way to the measurement time, which I called the output time above. From here we can simply deduce the S operator. We know that the probability of a scattering particle arriving in a particular final state is simply the leftmost value in the following equation. I explained above that if we take the initial state, time evolved all the way to infinity, we end up with a superposition of possible states, and if we want to see the probability amplitude of a particular final output state, we just take the inner product of that particular final eigenstate with the infinitely time evolved input state. We know we can do that with this time evolution operator where the integration limits are taken to be negative infinity to positive infinity, and we also know that it's the definition of the S operator to do exactly that. Therefore, the U operator, this time-ordered exponential for the case of integrating from t equals negative infinity to t equals positive infinity, is just the S operator. Therefore, we now have a well-defined expression for the S operator, one in terms of this convenient time-ordered exponential. We can also write it in terms of the Hamiltonian density if we like there, in which case we're integrating over all of space-time instead of just all of time. With the S operator completely characterized, we can now claim, in some sense, complete understanding of the S matrix, which is just the initial and final state matrix elements of the S operator. We have now derived the S operator and the S matrix from the interaction picture. Our work is done. You have now seen how the interaction picture allows both the states and the operators to time evolve, and does it in a clever way. It describes the time evolution of the operators exclusively with the free Hamiltonian, and the evolution of the state vectors exclusively with the interacting Hamiltonian. This allows interactions to be accounted for in a mathematically handleable way. It's one of the most important ways of representing quantum field theory. It yields a convenient expression for the S operator. It ends up being a time-ordered exponential of a time integral of the interacting Hamiltonian in the interaction picture, where the interacting quantum fields in the interaction picture, in terms of which it's written, have the mathematical structure of free fields, therefore rendering the math tractable. Of course, you need a few more steps, like the LSZ reduction and the Wick expansion, but of course, you can't handle everything in one video. I hope this video helped you understand such a key piece of quantum field theory better. I hope you enjoyed it. If you did, please give it a thumbs up, and don't forget to subscribe. Dietrich out.